All right, welcome everybody to this week's GOCC. Um, Before we get started with the great talk, I just want to remind everybody of our community statement. So we follow three guiding principles. The first is we're all learning. So we encourage you to ask questions, make use of the chat, and one of us, maybe most likely Alex, will interrupt and jump in and ask the question. Um, I think Alex is just better at doing that than I am. I don't know. I'm very awkward. I don't know where to stop people. Um, the second one is that everyone has something to contribute. So we all approach combinatorics a little bit differently. So if you have something that you want to share or have questions and want some clarification, again, please use the chat. And I'm sure one of us has an answer or some direction or know somebody that we could ask. And the last one is no one has all the answers, not even the speakers. So part of this is that we are learning together. And so there might be things that stump us, but again, we are a community of scholars. And so I'm sure we can work towards getting an answer or somebody that knows the answer. And with that, it's my pleasure to welcome Will Gustafson from the University of Kentucky, and he'll be talking to us about lattice minors and Eulerian posets. So let's welcome Will.
Thank you. Okay, so the main goal of this talk here is to introduce the definition of deletion and contraction on lattices, which will in some sense generalize deletion and contraction on graphs. And then from this notion of deletion and contraction, I'll define a poset of minors for any lattice. And then I'll give a construction which shows that these posets are Eulerian and that they have nice topology. Okay, but to get started, I want to real quickly recall the definition of an Eulerian poset and then give a little bit of motivation, show you where this idea came from. Okay, okay, thanks. All right, the annotations. All right, okay, so Eulerian poset is a graded poset with a minimal element and a maximal element. And then for all x less than y, it has to satisfy this condition here. So this is just saying in every interval, there's an equal number of odd and even rank elements. Again, really the motivating example is the face lattices of polytopes. So these famously satisfy the Euler-Poincare relation. And this condition here is really just saying that an Eulerian poset satisfies that same relation on every interval. More generally, we have face posets of regular CW spheres as Eulerian posets. So it's that's a big class of geometric examples. And then in a more algebraic flavor, we have intervals of Bruhat orders as Eulerian posets. Okay. So now where this idea for deletion contraction on lattices came from is from a particular Eulerian poset called the Uncrossing Postsets. Let me tell you a little bit about that now. Okay, so the Uncrossing poset is a poset on pairings of the set 1 to 2n. So this is the n equals 3 case here. So we can represent pairings with these diagrams here called a medial graph. We just have the points on a circle and then connect up what points are paired. So this is the pairing 1 to 4, 2 and 5, and 3, 6. Okay, and then loosely speaking, the order relation in this poset is that we go down by uncrossing these intersections in one of two ways. Right, so if we have a crossing like this, we can either resolve it like this or like this. Okay, yeah, so this is actually a really interesting poset. It has a lot of cool combinatorics and some nice structures. Let me tell you a little bit about that. So just some enumerative information is that this is graded by the number of crossings and then +1 because of that minimal element. So in particular, it's rank n choose 2 because the top element has all n arcs crossing each other. The number of pairings, number of elements in this poset is a product of first n odd numbers, and there's Catalan mini atoms as well. Right? These correspond to non-crossing chord diagrams, which is a classical Catalan object. Okay, and there's also connections to type A Bruhat order. And there's more to be said about the Catalan combinatorics. So there's some neat combinatorics going on here. Okay, and so this poset is indeed Eulerian, though showed by Thomas Lamb. So it's actually like not so trivial, not so easy to see. Took a lot of work, or maybe not a lot of work, but took some work. And Hirsch and Kenyon showed that this poset is shellable, so that means the order complex of this poset has a Schelling order, and from that deduce that it's a CW poset, which is to say that this is isomorphic to the face poset of some regular cell complex. Okay, so it's also like very, geometric object if you want to view it that way. Okay, but what does this all have to do with deletion and contraction?
We have a quick question in the chat.
Yeah.
So Galen's asking, just for clarification, Eulerian also means mu 0x is plus or minus 1, correct?
Yeah, but a little bit more than just 0x. It has to be, you have to do it on all intervals. So the statement is the Mobius function is like the -1 to the rank difference of the things you inputted. Okay. Yeah, so what does this poset have to do with deletion contraction though? Well, this poset first arose as the face poset of a stratification of a certain place of planar electrical networks. And through this correspondence, these pairings are in bijection with certain equivalence classes of graphs. Okay, so I'll show you a figure, tell you a little bit about that. Okay, so, right, so this is that same poset, and then I've drawn like a particular representative of this equivalence class of graphs. So first, let me tell you how you construct this. So, well, the equivalence class of graphs, each graph corresponds to like a different embedding of these medial graphs. You can move the arcs around and that would change the graph somewhat. But the construction to get this graph representative is we place endpoints along the boundary, 1 between 1 and 2, 2 between 3 and 4, and so on. And then you have an edge for each crossing of the medial graph. Okay, and then there's one other little tricky thing. So if you look at like one of these, right, this is shrunk up because when you put these points on the boundary, 1 and 3 will be in the same region of the medial graph. And when that happens, we just, the construction is that those points get identified. And so we're sort of like taking the circle. It's like 1 and 3 are in the same region, so we pinch it off. Okay, so that's what you're looking at here. Okay, and I don't want to go into details about these equivalence classes of the graphs, but it's enough for the purposes here that if you look at a lower interval like this, where the top element has a graph with all the vertices on the boundary, none of them in the middle here, the blue vertices, then you can look at just representatives, which are minors of this graph. And then the equivalence classes are like simplifications. So if you just look at the blue graphs here, you can see that this poset is like the poset of minors of this 3 cycle, and then like collapsed under simplification. So it's a poset of simple minors of this 3 cycle, and it's with respect to a vertex labeling. The edges aren't labeled. Okay, so yes, this is like a motivating example of the uncrossing poset here. Since we know it has nice structure, we see that any graph that you can embed planarly with its vertices on the boundary, like this top one, this poset of minors that I described will be Eulerian and will also be a CW sphere. So it's like, really nice. And if you want to, try and study these posets of minors of graphs and learn more about them, well, it just kind of turns out that the right viewpoint happens to be lattice theory. Okay. All right, so hopefully now we're all like sufficiently motivated, and so now I'm going to go into setting up some definitions and talk about this deletion and contraction for lattices. All right, so definition of a lattice here is just a poset, and any two elements have a join or least upper bound and a meet or a greatest lower bound. Right, and that's what that means in symbols. Okay, and the other important thing here will be a join irreducible. This is an element in the poset which covers exactly one other thing. And so this name, this is like a usual notion of algebraic irreducibility. If you want to write such an element as a join, then it really has to be one of the things in the join. Okay, and then one note is that I'm only considering finite lattices here. Okay, so this is a small example of a lattice. Here, the join irreducibles are A, B, and C. Okay, we'll come back to this example later. All right, so now I can tell you what deletion and contraction is on lattices. But first, real quick, this is, so it's defined for something with a little bit more structure than just a lattice, but a lattice together with a generating set. And when I say generating set, I mean a set which contains a minimal element and which generates the lattice under joins like this. Okay, I'm going to use angle brackets to denote that. It kind of assumes a join operation, but that will always be clear. Okay, so then with that, the contraction of a lattice L with a given generating set by a subset I of the non-minimal generators is this lattice with generating set here. So you should just think we take all the generators of L and sort of lift them up by everything in I. Okay, then the deletion is this lattice with generating set. You just remove all the generators in I. All right, and then when I say minor of L, I just mean everything you get from L by deletion contractions. Okay, so let's look at a couple examples now. All right, so in the top left here, this is face lattice of the square. And our generating set I'm taking to be the atoms and the minimal element. Oh, so I wanted to point this out. With the generating sets, you always have to contain all the join irreducibles and the minimal element. So that's like a minimal generating set for a given lattice. Okay, but here's a lattice. And if we take the deletion by 1, well, we get this thing here. This lattice of generating set. So we, of course, lose 1. And we also lose these two elements here since they can't be written as a join of just 2, 3, and 4. Okay, and then down in the bottom left, this is the lattice with generating set we get from contraction by 1. So you can see it looks like the upper interval above 1, or it is rather. And yes, and here's our generating set, right? So we get 1 just coming from 0 hat and 1. And then 1, 2 come from 1 join 2, 1, 3 from 1 join 3. And then we also get 1, 2, 3, 4 as a generator from 1 join 4. Okay, and then if we take, excuse me, if we take this minor and delete the generator 1, 2, 3, 4, well, we get this over here. So this is the same underlying lattice, but now with a different generating set. So we still have 1, 2, 3, 4 since it's the join of these two, but now it's not a generator. And so these are really being considered as two different minors since they have different generating sets, even though they're the same lattice.
And we have a quick question from Galen.
Yeah.
Does this have a nicer description on supersolvable lattices?
I don't know. I don't know a lot about supersolvable lattices, but that might be a good thing to look into. Thanks. Okay, right. So our main motivation was these vertex labeled simple minors of a graph. So, why does this really capture that? Let me talk about that. Okay, so we have this statement here. If we have a graph G, we give it a vertex labeling and look at its lattice of flats. Then the simple vertex labeled minors of our graph are in bijection with the minors of the lattice of flats. And the bijection is what you want it to be. You just take the lattice of flats of the graph minor. Okay, so let me give you an idea of how this bijection works. So, where's my mouse? Oh, here it is. Okay, so if we have this graph over here, and then this is this lattice of flats. So I've written these as partitions. These are just all the partitions you get as connected components of this graph. So for example, 1, 2, 3/4 here, that gives the connected components of the subgraph 1, 2, and 1, 3. All right, and then down in the bottom left, this is the graph, the simplification of the graph we get after contracting the edge 1 to 2. And this is the associated lattice of flats. You can see it's a contraction by this atom here. And over here, this is deletion by 3, 4 of the graph, and then the lattice of flats. And you can see it's the deletion of this atom in the lattice for the original graph. Okay, and then the idea of the inverse bijection going from a lattice minor back to a graph is that the minimal element here will tell you what the vertex labeling is. Right? So 1 and 2 are together, so 1 and 2 are together, 3 and 4 are separate. And then each of these atoms will tell you the edges. So in this lattice, you get these atoms from the minimal element by merging 2 of the blocks. And so it tells you in the graph that those 2 blocks, which are associated with the vertices, are connected by an edge. And then the simple restricting to simple minors comes in because the lattice really only encodes simple information. There's no way to encode in this way 2 edges, or like a multi-edge, I mean, or a loop. All right. So the main object that I want to tell you about today is the poset of minors of a lattice, or rather a lattice of a generating set. Okay, so this is just a set of all minors of the lattice, and then we have this partial order on the minors, which is just saying that you go down in this poset by deletion and contraction. And then I'm also going to add a minimal element and call it empty set, so we don't get mixed up with the 0 hat of the lattice. Okay, I'm denoting this by ML. Okay, so here's an example. So there's that lattice from before, and as the generators, I'm just taking 0, A, B, and C. Okay, so if you look at the coatoms, for instance, this is a deletion by C and the deletion by B. Here's a deletion by A, and then this is contraction by A. So where did contraction by B and C go? They're down here. So contraction by B, why is that lower rank? Well, when you contract by B here, A will go to B. So you could have deleted or contracted A beforehand, so that puts it lower rank. And here is similar, but a little bit different thing happens with contraction by C. You join everything by C here, A and B both go to the 1 hat. So you could have deleted A or B first, so that puts it a lower rank.
And we have another Galen question.
Yeah.
Is there a special rule about deleting and contracting when you have a loop or co-loop in the graph case?
So since we're looking at the lattice of flats, a loop doesn't show up at all, right? You can just look at the simplification of the graph anyways. And co-loops, there's not any sort of special rules about co-loops.
But specifically, if you had a loop in the graph, you would just ignore it because it wouldn't show up in the lattice of flats. It's only the simplification. Okay.
Okay, and then 2 other things I wanted to point out in this poset real quick is that this is graded by the number of generators. Here's 4, 3, 2, and 1 generators. And the atoms, you'll notice, are exactly the elements of this lattice. Okay, so now I want to give a couple just basic results about these posets in hopes that will give a little bit of intuition for these. And then I'll talk about this construction. All right, so this first result here, first 2 things are what I just pointed out. The atoms are always going to correspond to the elements, and it's always graded by the number of generators. And the rank 2 elements of the poset of minors are not so hard to describe. So you pick one element as your bottom set, anything in the lattice, and then you pick a joint irreducible to go up by. Okay, and then these are also thin, meaning every rank 2 interval looks like a diamond. Okay, and then the second proposition here, it gives us a different way to think about the minors. So quick aside first, if you think about this notion of deletion contraction, it's really only using the join operation of our lattice, not the meet operation. So maybe that suggests you should really be thinking about these as instead join semi-lattices with a minimal element. And I mean, they're finite anyway, so that's still a lattice, but the difference that makes is now, the free object is the Boolean algebra. So minors you can think of as, a structure inherited from the intervals of the Boolean algebra. Okay, and so what I mean technically by that is, if we look at this canonical map from the Boolean algebra to your lattice, where we just send a set to the corresponding join of irreducibles, or sorry, generators, then the minors of the lattice are exactly the images of the intervals of the Boolean algebra. And so, I have to tell you what the generators are for a minor, and those are just the images of, well, the generators of the interval you picked, which are the atoms in that case. Okay, and then in particular, if you look at the Boolean algebra itself, well, the minors are just its intervals. And then from that, the poset of minors will be the interval poset of the Boolean algebra, which is the lattice of flats of the cube of dimension n. All right, so that'll come into play later. Okay, so two more results here, which maybe you could think these could be useful for identifying these posets of minors if they're showing up in the skies maybe. So the first one here says if we look at this interval from the minimal element up to the top, which this is going to consist of exactly the deletions of L, because whenever you contract, you need the bottom element. But this interval is isomorphic to the Boolean algebra. Okay, and then also if you look at just the contractions, which is not going to be an interval, but if you just look at contractions, this subposet is isomorphic to the dual of the lattice. So that you can just think when you contract, you're going down by moving the bottom element up. So that's why it shows up as the lattice dual. Okay, but maybe that's useful for identifying these because that posets of minor posets always have to contain a large Boolean algebra here, and in particular, you have to have at least n coatoms if you have n+1 generators. Okay. So the second proposition here, well, the first part is what I said on the last slide, that the minor poset of the Boolean algebra is exactly the face lattice of the n-dimensional cube. The second one here is if you look at a chain, the minor poset you get is the Boolean algebra now of one rank up. Okay, and I've got a little picture how you might see that. So if you start with a chain here, if you delete a generator, you just can remove anything except the minimal element, and you get another chain. If you contract by the atom, you get rid of the 0 hat, and you get another chain. So these covers are exactly the covers of the Boolean algebra of rank 1 higher. Okay, and then these two propositions will imply that any rank 3 lower interval in a poset of minors has to be either the rank 3 Boolean algebra or the face lattice of the two-dimensional cube. Right, so this just follows because if you look at a lower interval in a poset of minors, it'll be the poset of minors of that minor, which is the top element. And there's only these two lattices, the chain and a rank 2 Boolean algebra, which have only 3 generators. Okay, so yeah, so now I'm ready to go into this construction for you. But first I need to set up a couple definitions and theorems for that. Okay, so we say poset is a PL sphere if the order complex, when you remove the minimal and maximal elements, has a piecewise linear homeomorphism from that order complex onto the boundary of its simplex. Okay, and large classes of examples of this are the face lattices of polytopes, and a little bit more interestingly, the intervals of Bruchau intervals. So that was proved by Nathan Redding. Okay, and then it'll be useful to note for later that the interval in a poset, which is a PL sphere, is itself a PL sphere. All right. The other thing we'll need is this zip operation of Nathan writings. Okay, so we say an element in a poset is a zipper if it covers exactly 2 elements. Those 2 elements have the same downset, and it's also the join of those 2. And then when we have a zipper, we can look at this poset zip PZ, which we get just by identifying those 3 elements. Okay, so here are some pictures illustrating that. So on the left here, this is what a zipper looks like in the Haas diagram. And then in the zip poset, right, that's what the Haas diagram will look like. We identified those 3 elements. And then on the right, if your poset was a CW poset, this is what it looks like geometrically. So on the complex. Yeah, so we'll have, cell Z, which has 2 cells, X and Y, making up its boundary. And then this downset condition says furthermore that those 2 cells have the same boundary. And then when we zip them, you can just think we contract this cell Y, and that pulls together and identifies the other cells X and Y. Okay, but it's not just like any cell contractions. We have this join condition. So these will come together to make sure that the poset we get stays rather nice. Okay, then one thing I want to point out is if your poset P happens to be thin, then this second condition follows for free. So you only have to check the first and the third actually. So I can simplify things. Okay, but so Nathan Redding introduced this operation and then proved that it preserves Eulerianness and PL sphericity. Right, so this is how we're going to get that these posets of minors are Eulerian and PL spheres. Right, and just as a historical note, I want to say when Nathan Redding introduced this zip operation, it was to study intervals in Bruja orders, and he used it to get a structural recursion for them and a recursion for something called the CD index as well. Right, so that's kind of like why it was introduced. Okay, so now I'll give you the statement of this construction here. So we start with lattices L and K, so that there's a join preserving surjection from L onto K, and then it also sends the generators of L onto the generators of K. Okay, so this is like a join preserving and generating set preserving surjection, you could think. Okay, but when we have that, then the statement is that the poset of minors of K can be obtained from the poset of minors of L by a sequence of these zip operations. Right, and then as a corollary to this, we get that any poset of minors is Eulerian and a PL sphere. So this is coming from the fact that the Boolean algebra has a map like this onto any lattice. It's a map we wrote down earlier, where you send a set to corresponding join of irreducibles, or generators, sorry. And its poset is the face lattice of cube, which is itself Eulerian and PL sphere. Okay, so now I want to give you like just a little bit of an idea how this proof goes. All right, so if we let F be this map from the hypotheses in the theorem, right, then the first idea is that we're going to view that map instead as a congruence on the original lattice. Okay, so that's what I've depicted here. We have the rank 3 Boolean algebra, and we map 1 to A, 2 to B, and 3 to C in this lattice here. Then as a congruence on this Boolean algebra, it looks like this. So in blue, I've got the fibers of each thing, and the blue lines here say these are congruent because they're getting sent to the same thing. Okay, and then the idea is that we're going to build up our lattice that we want to get to over here. Or let me say, we want to build up this congruence on a lattice sort of one edge at a time. Right, so by first identifying these 2, and then these 2, like that. But as we do that, we have to be careful in what order we add the edges. Like if we start by identifying these 2, this won't preserve joins. Okay, but a congruence is going to preserve joins when the edges that are congruent, so these colored edges, form a lower order ideal in this poset here on edges. So loosely, this is saying you go down in this poset by sort of lifting your edges with a lattice element like this. Okay, so that's what I've got over here. This is the poset of edges from the Boolean algebra. And in blue, I've got highlighted our blue edges from here. All right, so the idea is we're going to add these edges in some linear extension going up this poset. And so now if we just apply induction, we can just look at the case where we only have to add one edge. So that means that this map F has one non-trivial fiber, X covered by Y. And if you think about this condition here, the edge being minimal in the poset, this is going to happen exactly when X is covered only by Y. All right, so just to summarize again, now we've reduced to the case that this map F has one non-trivial fiber consisting of X, which is only covered by Y. All right, so now we want to see what happens when we apply that sort of map. All right, and then so we're going to look at F applied to minors just by applying it to its generating set. And when we do that, the fibers are exactly these triplets, where M has both X and Y as generators, and then MY, we remove Y as a generator, and MX, we remove X as a generator. And since X is less than Y, it could be the 0 element. So there's potentially 2 ways to do that. All right, so it's pretty obvious that these 3 minors will get mapped to the same thing by F. The converse, that whenever you have 2 things being mapped to the same thing by F, it's in one of these triplets. Takes a little bit of work, but it's not too bad. Okay, and then the last step here is just to show that each of these minors M are going to be zipper when we go up rank by rank. So we start by zipping the rank 2 minor with X and Y, and then we'll go up in ranks. So remember, there's 2 things that we need to check, only 2 since the poset of minors is thin and thinness is preserved by zipping actually. And those things are that M only covers these 2 things and that it's a join of these 2. And don't want to go into a lot of details, but the fact that it only covers these 2 is just kind of by construction. Once we get up to M, we've already zipped everything below it with both X and Y as generators, so it only has MX and MY left. And the fact that it's a join comes from, you can show that this is the join in the poset of minors that you started with, ML, and when you get up to M, you haven't zipped above it, so that isn't messed up. Okay, so yeah, that finishes the proof ideas. So now I want to show you like a little drawing of how this construction sort of plays out. Okay, so at the top, this is that Boolean algebra, the congruence again, that same lattice. Just below it here, this is just the cube, with the same edges highlighted. So these are the edges we'll need to zip to get down to the complex whose face poset is the poset of minors of this lattice. So to start with, we have to, on the lattice, we're going to start by identifying either these 2 or these 2. I chose to identify 2, 3, and 1, 2, 3 first. And so on the complex here, we zip this edge, and then that looks like this. So track that, and then we get this funny thing with a square wrapping around. So this complex has face poset, the poset of minors of this lattice. Okay, and then the next step, so I identified these 2 elements, could have done these 2, but I did these 2 next. And then so on the complex, we have to zip this edge, and that gets us here. So it's getting a little hard to read at this point, but there's like a square wrapping around with a 2-gon on this back right side. Okay, and then we actually have to zip this 2-gon as well. So this corresponds to the minor here with these 3 elements, and both of these are generators, and that's what we're identifying. So we zip that 2-gon to identify those 2 edges, and that gets us to a complex like this. So there's a square wrapping around on the right side there. Okay, and the face poset of this complex is the poset of minors of this lattice. And then the last step is to identify these 2 elements. So we just zip this edge to get this complex. And then we have this 2-gon on top, which again, we need to zip. That's coming from the minor with these 3 elements. So both of those things are generators. So we zip it to get this complex. Okay. So maybe that's a little hard to visualize, but there's like a square on bottom, another square on top, and then these 2 triangles. And the face poset of this complex is the poset of minors of this lattice here. Okay, so last thing I want to do is talk about some CD index inequalities you get from this construction here. So yeah, first I'll review what the CD index is. Okay, so if we have a rank n plus 1 poset with minimal element and maximal element, then we define first the AB index in this way. So we have non-commutative variables A and B, and then we define these weights for every chain. So you get a B for every rank you do go through, and then an A minus B for every rank the chain does not go through. Okay, and then the AB index is just the sum of all those weights over all the chains. The CD index is a like, that's the right word, I don't know, transformation of variables, yes. So we let C equal A plus B, D equal AB plus BA. And if we can rewrite this polynomial in terms of C and D, then that's the CD index of the poset. It's not always possible to do that. It's kind of a special thing. It's pretty easy to find posets that don't have a CD index. But okay, but a theorem of Baron-Bellers states that if your poset is Eulerian, then it does have a CD index. Okay, and so here's a example of a CD index for you. So here's all the chains in the rank 3 Boolean algebra, and then there's their chain weights. So just sum over all the weights for all the chains. When you expand that out, you get this product here, or sorry, this polynomial. So that's the AB index, and then in this case, we can write it as C squared plus D. So that's the CD index of the rank 3 Boolean algebra. Okay, so since the posets of minors of lattices are Eulerian, we know they have CD indices, and the zip construction actually gives us some inequalities. So I'll need some theorems for that. So the first one here, we have this non-negativity result of Caru's, that if you have a Gorenstein star poset, the CD index has non-negative coefficients. So here Gorenstein star means an Eulerian poset whose order complex without the 0 hat and 1 hat is has the homology of a sphere. Okay, so that's like very abstract, but in particular, if we have an Eulerian poset, which is a sphere, then the CD index is non-negative. And recall the posets of minors of lattices are PL spheres, some particular spheres. All right, and then when Nathan Redding introduced the zip operation, he gave this formula for how it affects the CD index. So you subtract off the CD index of some intervals here with a, with the coefficient. Okay, and right, but that only works if your zipper isn't the top element. Excuse me. And if it is the top element, well, it's much simpler. It's rather easy to compute, but you lose a factor of C on the right. Okay. So now, just using the results on the last page in the PL sphericity, we get this corollary. So under the same assumptions as the term before, this join preserving surjection from L to K, and it sends generators of L onto generators of K. Well, we get this inequality here. So you should think that it's really just the minor poset of K has a term-wise CD index smaller than minor poset of L. But if K has less generators, then they're different dimensions, and these polynomials are like homogeneous with degree, the rank, when C has degree 1, D degree 2. So the point is, like, if you have different number of generators, it doesn't make a whole lot of sense, but there's this factor of C that corrects that. Okay, and then also any positive minors has seed index smaller than the cube, since we can start with the cube and zip down to them. Okay, and then here's just like a smaller example. In that lattice before, you can see its CD index is smaller than Boolean algebra. Okay, so that's all I have for you guys today.
Awesome. Let's thank Will for the talk. Great. Are there any questions for Will? I know there's some already in the queue in the chat.
Yeah. Can I ask a question?
Yes, go ahead.
Okay. So I was curious a little bit. So I know that you have all this stuff with CD indices and all this stuff with the zip operation, but just rewinding quickly to this L star result that you can read off the dual lattice from your lattice of order ideals or of deletion contraction. I don't know if you've thought at all about the chromatic polynomial of your graph, but if you have a graph, you can, and this is why I asked this co-loop question or loop question, because when you have a graph, you can do deletion and contraction on the graph, and you can recover the chromatic polynomial and some other polynomials that maybe not graph theorists like, but that matroids people like. And I'm curious if you have thought about being able to read off any of those polynomials from that L star. I mean, you could just take like the lattice you like, flip it upside down or something, but.
So are you thinking like recursions for these polynomials via deletion contraction, or like reading it off the poset somehow instead, positive minors?
Well, I think you could probably, you can almost certainly read it off of L star of that poset. You can read like the chromatic polynomial from L star, the chromatic polynomial of the dual graph from L star, if, under a certain set of assumptions. But I was wondering if from the poset, you can also read off the deletion contraction recurrence.
That's a good question. Yeah, it's not something I've thought about, but it's a good thing to look into.
Are there any other questions?
I have another question if there aren't other questions, but maybe I can wait.
Go ahead, Galen.
Okay.
Maybe you'll inspire other people to ask questions.
Do you know if, like in your graph case, okay, so you have a graph and you know that there's two graphs whose lattice of flats, you can go between them by zip operations. Or you can do your zip, you can connect these two lattice of flats. I can't remember if you wanted to do the deletion contraction operation and then connect them via the thing, but you can go between the correct poset for graph A and for graph B. Do you know that graph A and graph B have to have some kind of similarity?
So, I mean, the statement for the lattices was there's a join, preserving surjection, and it sends the generators onto the generators. So for graphs, we like have a join, preserving surjection on lattice of flats, and then all the atoms would go to atoms or the minimal elements. This is like a strong map of matroids if you want to think about their matroids. And what that means graphically,
Because it means they've got
it
this.
should be, I believe it's at like every flat in the target lattice. Yeah, when you pull back to where you started, that would be a flat as well.
Okay.
So like flats come from flats in the graph case. Not sure if you can say more than that though.
Cool.
I don't know if that's the kind of thing you were thinking of or not.
Yeah. I would have also, in interest if there are graph statistics that are preserved under this thing. So if, for example, so it's possible that like what you just said already has a meaning in terms of the graph, but it also might mean that like, you know that they have, you know, every clique of the graph must be contained in a bigger clique. You know, there's it's sort of like graphical things that we'll care about.
Yeah. Maybe.
Awesome. Are there any other questions? All right. Well, before we thank the speaker one last time, let me invite you to next week's GOCC. We will have, oh my goodness, I had it pulled up and I closed it.
Is Colin next week?
Yeah, Colin is next week. And Colin will be talking about stack sorting for Coxeter groups.